Hello students, welcome to reading.com. In this video, we are going to study about computer vision. First unit title is Image Processing Foundation. In this unit, we are going to start with very basics of how computers work with images. We begin with fundamental operations that takes raw image data and make it ready for more advanced computer vision tasks. First, we look at classical filtering methods. These help us smooth or sharpen images depending upon what we need. Then we will explore thresholding, which is a simple but powerful way to convert a grayscale image into black and white image. Next, we will study about edge detection. It finds the object boundaries, and then corner and interest point detection, which are very important for some tasks like image matching and 3D reconstructions. We will also talk about mathematical morphology. These are all the tools that help us with the shapes in images. And finally, texture analysis, which is about recognizing surface patterns. By the end of the unit, we will conclude all the fundamental concepts that are related to our computer vision subject. Now we can see the definition for the computer vision. It is a branch of artificial intelligence that teaches machine to understand and process visual information just like we human do with our eyes and brain. The main goal here is to mimic human vision. That means getting computers to recognize objects, detect things happening in a scene, and even track movements over time. And the computer vision can be used in different areas. In security systems, it helps spot faces so devices can recognize people. In self-driving cars, it's part of how the car detects and tracks objects on the road. Doctors use it in medical imaging to outline important detail in scans, and in factories or robotics, it is used to check product quality and guide missions. The computer vision mostly relies on image processing. So let's see what is image. Image is nothing but a picture information. But in computer point of view, image is a collection of pixels that can be arranged in row and column wise. These collection of pixels are represented as a corresponding numbers. If it is a color image, the information can be stored as the combination of RGB value numbers. If it is a black and white image, the numbers can be represented as black, white and different shades of gray colors. So, in the computer point of view, any information can be stored as numbers only. The first concept is classical filtering. Classical filtering just means adjusting the pixels in an image to clean it up. Instead of working on whole image at once, we look at small regions like little neighborhood of pixels and apply some math to adjust their values. This method is useful for some tasks like smoothing out rough areas, sharpening details, or detecting edges, which are all building blocks of bigger computer vision jobs. Filters can be categorized into different ways. First type is linear filters. These are all different types of linear filters. Second category is non-linear filters. Third category is frequency related filter, that is called frequency domain filters. Apart from that, edge detection filters and adaptive filters also there. In upcoming slides, I am going to explain what is mean filter and Gaussian filter. Let's take one example image. The image can be represented as number, 0 represented as pure black, 255 represented as pure white, the value in between represented as different shades of grey color. If we try to draw the image from this value, that image looks like this. I already told the image can be represented as row wise and column wise. There are 5 rows and 5 columns are there. Now I am going to apply the mean filter operation. If I take this pixel value, I am going to take the average of the surrounding pixel values. But in case of the first pixel value, the surrounding pixel values are only 3. To avoid this, add 0 to the surrounding of this picture information. it looks like this. So the original image information is there. I add 0 to the surrounding of this image information. This process is called zero padding. So the original image is 5 by 5 matrix. After applying the zero padding, it becomes 7 by 7 matrix. And the first value can be represented here. And the surrounding elements are 000, 000, 00 and 50. Now I am taking the average of these value including the center point. The total value is 50 divided by 9. The value is 5.5. I am going to round this value. That value is 6. So instead of 0, the resultant image contained the first pixel value as 6. The second number represented here, the surrounding values are there. I am taking the average for these values. The average value is 11.11. After rounding, it becomes 11. In the same way, third value can be calculated. Next value. So it becomes 11.11. And next value, it becomes 5.5. So if you get the fraction value, it should be rounded into a full number. In the same way, we can calculate all the pixels value. Let's check what happened if the pixel value when we check at the center. So the surrounding values are there. So if we calculate the average, it becomes 56. In the same way, we can repeat this operation for all the pixels value and finally find the final result value. I try to draw the image from this value. It looks like this. So this is the output of the mean filter. Actually, the given image having the noise at the center that can be reduced by means of mean filter. Let's take one real example. In this photograph, it contains so many noises. If you are applying the mean filter, the output looks like this. So this is the application of mean filter. Then go for the Gaussian filter. I am taking an original image. It has some picture information and I purposely add two noises. These noises are usually called salt and pepper noise. After applying the Gaussian filter, the output image looks like this. That means the noise can be reduced. This Gaussian filter is otherwise called improvised version of mean or average filter. That means it gives better results than mean or average filter. First we understand the meaning for the Gaussian filter. The Gaussian function is a bell-shaped curve. That means the center point is having the more value. So the kernel can be designed like this. The corner values are low values and middle values having the high value. So this is the common value for the Gaussian filter. Let's see one example. How this image can be converted into this image. So this is the original image having the noise information. Now we are going to apply the Gaussian function over this image values. I already told if you are choosing this image, the surrounding pixels are only 3. To avoid this, we are applying the zero padding before going to do the mathematical calculation. So after applying the zero padding, this 5 by 5 matrix becomes 7 by 7 matrix. Now we are going to apply the Gaussian function from this image. First I take the initial value that can be present in 0, 0th location. So 0th, 0th location located here. The surrounding elements are there. Now I am going to multiply this Gaussian filter kernel value with this matrix. So 0 into 1, this is the first value, plus 0 into 2, plus 0 into 1. So in this way I am going to multiply all these matrix value one by one. Finally I got 480. After dividing 16, I can get 30. So this is the new value for this 0, 0th location. In the same way, I am going to take the 0, first location. This is the actual pixel. So surrounding values are there. Now I am going to multiply this pixel values with this Gaussian filter kernel. So 0 into 1, this is the first value, plus 0 into 2, plus 0 into 1. So in this way I am going to multiply all these values. And finally I can get 60. After dividing 16, I can get 37.5. It is rounded into 38. So the second value can be replaced as 38. So in this way, you can move this slide over all the pixels and calculate the corresponding new values. That can be listed here. So if you try to draw the picture from this information, it looks like this. So after applying the Gaussian filter, this noise can be reduced. I hope you understand now how the filters can involve the picture information and change into another format. So this filter can be usually reduce the noises present in the picture information. Let's move to the next topic called thresholding techniques. Thresholding is one of the simplest way to separate objects from the background in an image. Basically, we pick a cutoff value. If a pixel is brighter than that, we turn it white. Otherwise, we turn it black. So, the image becomes just black and white, which makes it much easier to analyze. It is like drawing a line and saying anything above this object, anything below this background. Thresholding is really useful because it helps us to separate the important objects from the background. It also makes the image much simpler, which means easier and faster analysis. That's why it is widely used in applications like OCR for reading text, document scanning, and even medical imaging. These are the different types of thresholding techniques: simple, adaptive, and Wurtz's thresholding. Before going to the example, I just try to explain the simple concept of thresholding. Let's take one simple image. It contains different colors. Black color represented as 0, pure white represented as 255. In between the color values can be give the different shades of gray color. I fix one threshold value as 100. It is purely randomly selected value. It can be selected depending upon the situation. Then I fix the rule: if the value is less than 100, that pixel value converted into black color. Remaining values is converted into white color. So these two pixels are comes under this category. Remaining pixels are comes under this category. So after applying this thresholding technique, the output image looks like this. So now we can treat this is the background image and this is the foreground image. So from this we can easily analyze what is the background and what are the foreground objects. Now let's see one actual example. The picture information can be represented as 5 by 5 matrix. The image can be looks like this. I can fix the threshold value 127. Now I fix the thresholding rules. Those pixel value less than 127, that becomes black color. Those pixel values greater than or equal to 127, that can be converted into white color. Now I am going to apply this rule for all pixels. For the first pixel, the value is 45. So 45 is less than 127. So it converted into 0. That means black color. The second pixel is 130. So it is greater than 127. So it is converted into white color. So after calculating all the values, the matrix looks like this. So this is the output after applying the thresholding. So the thresholding techniques convert the grayscale image into pure black and white image. Let's see one real-time example. If I want to analyze this image, first I remove the noises by apply different filter operations and then apply any one of the thresholding technique to get the binary image. This image is subjected to for further analysis. So the image processing next step is edge detection techniques. In the last section, we saw how thresholding makes an image simpler by turning into black and white based on intensity. This helps us isolate the objects from the background. So analysis becomes easier, but thresholding has limit. It only separates region. It does not actually show as the boundaries or shapes of the objects. That's why we need edge detection, which highlights those boundaries. Edge detection is a technique used to find points in an image where the brightness changes sharply. These points usually mark the edges of the objects. We use edge detection because it helps us outline the objects, extract meaningful features, and reduce the amount of data we need to process. It also plays a big role in improving tasks like segmentation, recognition, and tracking. Let's see one real-time example. I am going to focus this part of the image. Here, there are two different regions are there. One is sky and another one is tree. These two information can be separated by this line. So this is called an edge. For this picture information, the picture values can be suddenly changes here. So these changes can be identified as the boundary value. So this is the core concept of the edge detection. These are all the some common edge detection methods. In the next slide, I am going to explain how the Sobel edge detection method can identify the boundary of the object present in the image. In this example, if we traverse from top to bottom, the values cannot be changes. For example, 10 can be started here, all the values are 10. 200 can be started here, all the values are 200. So this image contains the vertical boundary. So if we traverse from left to right, there is a sudden change value can be happen. So first three values are 10, suddenly it becomes 200. So this is the boundary value. In the same way, all the values can be calculated. So this image contains the vertical boundary. So this vertical line we can easily identify ourselves, but by mathematical way we should identify there is a vertical line is there. For identifying this kind of edges, we are applying either horizontal or vertical Sobel operator. So this is a vertical edge. So I am going to apply the Sobel horizontal operator. So horizontal operator only identify the sudden changes of the vertical line. This kernel value looks like this. Before going to the calculation, let's we try to understand what is the meaning for this value. The left column has negative values and the right column has positive values. This setup emphasizes intensity differences between the left and right sides. So when we subtract them, we can detect vertical edges. The middle column is filled with zeros because we don't really care about the center. We only want the difference across the sides. And also the middle row is given higher weights like -2 and +2 since it is closer to the pixels we are analyzing. This makes its influence stronger and helps reduce noise while improving edge detection accuracy. And one more reason, the Sobel is basically combination of derivative filter as well as smoothing filter. The derivative filter identify the difference from left to right and smoothing filter having the higher value at the center. So the combination of these two looks like this. Now I am going to apply this horizontal Sobel operator to this given image. So before going to this operation, first I convert the original image into zero padding image. I already told the original picture information is there that can be surrounded by the zeros. Now I am going to apply this filter to this given image. First I take the first value. The first value is located here. Now these are all the surrounding elements. Now I am doing the matrix multiplication operation with this Sobel operator. So 0 into -1 plus 0 into 0 plus 0 into 1. In this way we can calculate the remaining values. So the value is 30. So the original value 10 can be replaced as 30 in the output image. In the same way, we can calculate the next pixel value. The next pixel value presented here. These are all the surrounding elements. Now we can do this multiplication and get the value is 0. So the second value becomes 0. So in this way, you can calculate the remaining values. Finally, we can get the value like this. Notice that most of the values are remain 0 or close to 0. But at the boundary between the dark and bright regions, we can get the large positive or negative values like 570 and -200. This shows that the Sobel operator is highlighting the vertical edges in the image. In other words, whether there is a sudden intensity change from left to right, the operator gives a strong response, helping us to detect edges clearly. So simply, Sobel horizontal operator highlights the vertical edges by detecting intensity changes between left and right. Suppose when we apply the vertical Sobel operator on the same input, we can get the very different output. You can see that most of the center rows remain 0, but the top and bottom rows very high positive and negative values. This happens because the vertical Sobel operator is designed to detect only horizontal edges. So the choice of Sobel operator depends on the type of the edges we want to detect. If the image has intensity changes from left to right, meaning vertical edges, we use the horizontal Sobel operator. If the images has intensity changes from top to bottom, meaning horizontal edges, we use the vertical Sobel operator. But in real world images, edges appears in many directions, not just vertical or horizontal. So we usually compute both horizontal as well as vertical operator functions and then combine them into the gradient magnitude. This way we capture all possible edge orientations, giving us a complete edge map of the image. The next topic is corner and interest point detection. In this unit, first we see the pre-processing steps, that means applying different filters to remove the noises. Next is thresholding, which helps us separate the regions of interest from the background. Then we move to the edge detection. Here we detect sharp intensity changes using operators like Sobel or Canny, which is highlighted object boundaries. After that, we focus on corners and interest points. These are special regions where intensity changes in multiple directions, such as points are stable, repeatable, and distinctive, making them very useful for analysis. Finally, we apply these techniques in various applications such as image matching, object tracking, and even 3D reconstruction. In simple words, edges are high change in one direction, either horizontal or vertical, but corners and interest points are high change in two directions simultaneously. And one of the application of corner and interest point detection is image matching. Let's see what is image matching by means of template matching. It is a technique used to find areas in an image that match a small patch called the template. This template usually contains a distinct feature like corner or interest point. The process is simple. First we choose the template from the image, then we slide the template across the entire image. At each position, we compare the template with the region of the image. Finally, if the similarity is high enough, we detect the match. This method is widely used for object detection and recognition tasks in computer vision. Let's see one example. I can take the image from the 5 by 5 matrix. The image looks like this, and I can choose the template that is small part compared to this image. Usually it is 3 by 3 matrix. That image looks like this. The template size is 3 by 3. So first I choose this 3 by 3 from this bigger image. This small part is called patch. Now I compare to this patch with this template and tabulate the values. The first value is 10. That can be compared with the template value 50. So 10 and 50 can be compared. These two values are different, so there is no match. And the second value is 10, second value is 100. That can be compared here and there is no match. In this way, we can compare each and every values. For these 9 values, these two values are matched. So the number of matches found are 2. That can be tabulated like this. Next, I slide to the next position. Here I compare this template with this patch. No values are similar, so I put 0 here. So in this way, I can calculate all the pixels values. Finally, I found only this value having the high matching pixels. That is, total pixels are 9. So all the pixels are matched here. So I understood the particular image can be present inside this big image. Let's see one real-time example. I want to find this image can really present in this large image or not. I can do the image matching with the patches present in the large image like this and tabulate the values and identify the particular image is present inside this image or not. The next topic is mathematical morphology. It is a framework of image processing techniques that are based on shape analysis. Originally, it was designed for binary images, but today it is also applied to grayscale and even color images. Why it is important means morphology helps us cleaning up noisy edges or thresholded images. It can fill gaps in contours and enhance the structure in binary image. Most importantly, it improves the accuracy of later steps like object detection, segmentation, and feature extraction. So, morphology acts like a supporting tool, making images cleaner and more structured for further analysis. These are all the different ways the mathematical morphology helps in different stages of the computer vision process. And the dilation is one of the morphological operation. Let's see one example. This image contains three ones. That means this is the foreground object, this is the background object. I want to apply this dilation only for these ones. So if I choose the square structure element means this is the middle element surrounded by all ones. So this is the first element means I can replace all the values, whatever the values present here, that becomes 1. So that can be happened here. And for the second one, these are all the surrounding elements. So the surrounding elements can be replaced into 1. So this can be happened here. For the third one, so the surrounding elements are becomes 1. So finally, after the applying the dilation using the square structured element, we can get the result like this. Suppose if we apply the vertical structure element, the first element is 1, the upper and lower elements are only ones. So I can change these two values one. In the second value, I can change these two values becomes 1. And third value, I can change these two value becomes 1. I don't bother about the right side and corner values. So after applying the vertical structure element, the dilation results looks like this. Suppose if we apply the horizontal structure element, we can get this value. Suppose if we apply the cross structural elements, that is only for the top, bottom, left and right values, ignoring the corner values. The output of the dilation looks like this. So depending upon the structure element, the dilation value can be differ. These are the properties for the dilation. The dilation expands the white regions or foreground in an image. This means objects appear larger after dilation. Second, it helps the bridge gaps. When two objects are close to each other, dilation can connect them, making them appear as one continuous object. Third, dilation smooths edges. It reduces sharpness along the boundaries and make the shapes looks smoother. Finally, the result of dilation depends on the structuring element or SE. The shape and size of the structuring element directly affect how much the object expands and in what direction the changes occur. One major use is in text recognition. Often scanned or old documents have broken characters. Dilation helps by making these broken characters, which improves the accuracy of text recognition systems. In medical imaging, dilation is used to connect different parts of organs in scans, making the structures more continuous and easier for doctors or automated systems to analyze. It is also applied in road or shape detection. For example, in satellite or aerial images, dilation joins the line segment so that roads, paths, or boundaries are more clearly identified. Finally, in post-edge detection, dilation enhances the detected edges, makes lines thicker and more visible for further processing or analysis. The next and last concept is texture. Texture refers to the spatial variation in intensity or color within a surface or region of an image. In simple terms, it describes the visual pattern or the arrangement of small surface elements which we call texels or texture elements. Unlike the single intensity value, texture focuses how intensity changes across the areas. The variation is what gives the sense of smoothness, roughness or patterns in an image and it very useful for analyzing and recognizing different objects or surfaces. And we should know the different approaches used in texture analysis. As we know, texture in an image refer to a visual patterns formed by the variation in pixel intensity. But in computer vision, we cannot simply rely on how the image looks to our eyes. We need systematic ways to study, describe and measure these textures. That's why the different approaches in texture analysis comes in. These techniques helps us convert the visual look and feel of texture into measurable number of features that a computer can understand. Once the texture is represented in a numerical form, it can be used for tasks such as classification, segmentation, or object recognition. So, texture analysis is essential about transforming visual pattern into data that can be processed and interpreted by the machines. Now let's look at two important approaches in texture analysis. The first one is autocorrelation. This method checks how similar texture looks when it is shifted. If the texture has repeating patterns, autocorrelation can capture the repetition very effectively. For example, it is useful in identifying regular structure like stripes or grids. In the second method is co-correlation matrix. This approach focuses on how often pairs of pixel intensities occur together in an image. By analyzing these co-occurrences, we can capture both repetition and the variation in texture, making it very powerful for describing complex surfaces. So, while autocorrelation highlights repeating patterns, the co-correlation matrix captures relationship between pixel values, giving us a deeper understanding of texture. Now I conclude what we studied here. Image processing techniques that transform raw images into meaningful informations. Filtering is the first step, used to enhance the image quality and highlight important features. Thresholding then separate objects from the background, preparing the imaging for the further analysis. Edge and corner detection follow, identifying the object boundaries and distinctive points, while morphological operations refine and clean these shapes. Finally, texture analysis describes surface patterns, completing the foundation for feature extraction in computer vision applications. Now the first unit ends. Don't forget to download the notes from the description section in this video. If you have any doubts or queries, feel free to leave them in the comments. And thank you for watching and learning with me. See you in the next session.